How do we physically apply a single qubit gate on a spin qubit? Well, to rotate a spin qubit, we can either move the electron very fast into magnetic field gradients, or we can apply current to generate an AC magnetic field which will interact with the spin of the electron. In both cases, what we need to apply electrically is a microwave signal at a frequency matching the Larmor frequency of the specific qubit. If we apply a microwave signal with the frequency matching the Larmor frequency of our qubit, the qubit will start rotating in the Bloch sphere around one axis, for example, the y-axis in this case. If we want to rotate the qubit around a different axis in the Bloch sphere, we have to change the phase of our microwave signal. For instance, before we were applying a cosine. Now we are applying, for example, a signal proportional to the sine in order to rotate around the x-axis. So, the phase of the microwave signal determines the axis of rotation. If we apply a certain amplitude to our microwave signal, the qubit will rotate in the Bloch sphere with a certain speed. If we increase the amplitude, the qubit will rotate faster, as shown here. To summarize, we have to generate a microwave signal with a frequency matching the qubit Larmor frequency, with the phase that determines the axis of rotation. We also have to take into account the amplitude and duration of the pulse, which determine the angle of rotation. To do so, we can do the following. We can first generate a signal which determines the duration and the amplitude. We can apply such a signal to a digital to analog converter, which converts such a signal from the analog domain to the digital domain. Then, if we multiply the signal with a sinusoidal signal, with the frequency and phase matching our requirements, we obtain exactly what we want, a pulse at a given frequency and phase, with the given amplitude and duration, which, when applied to a qubit, generates the wanted rotation of a given angle around the wanted axis. The parameters we pointed out, the frequency, the phase, the amplitude, and the duration, determine the angle and the axis of rotation. But how accurate should they be? Well, we can, for example, plot the infidelity of our qubit rotation, which is complementary to fidelity. It is just 1 minus the fidelity. And we plot that as a function of the relative error on the frequency, on the amplitude, and on the duration, and as a function of the phase error. Here, we want to have the fidelity of 99.9%, which means an infidelity of 10 to the power minus 3. We can find out how much accuracy we need for these parameters. For example, 2% for amplitude and time, 3% for frequency, and 1.80 degrees for phase accuracy. Now that we know the relation between the inaccuracy in each of these parameters and the infidelity, we could, for example, size our system, our microwave driver, to reach certain specifications. For instance, if we want to achieve a target fidelity of 99.9%, we could choose to divide equally the budget for infidelity over all these different sources of inaccuracy, which are the inaccuracy in frequency, in phase, in amplitude, and in duration, and the noise related to these parameters, which we have not talked about before. And these are the noise in frequency, in amplitude, in duration, and the white noise on top of the oscillator signal. For more details, please look at the reference paper. If you do this, we can get a system that achieves the target fidelity. We then have to design a system that achieves all these specific values for all the sources of inaccuracy and noise. Mind, however, the splitting or budgeting the infidelity equally over all the sources of errors is not always the best thing to do. For example, some specifications are very easy to achieve. In this case, achieving an accuracy in duration of 3 nanoseconds is extremely simple in today's technology. On the contrary, others may be more difficult to achieve, like the frequency noise or the amplitude noise. So what is typically done is to budget the error over all these parameters with the purpose of achieving a certain optimal performance of the system. This could be the complexity of the electronic system, the power dissipated, or the area occupied in an integrated circuit implementation. We have seen how to drive a single qubit with a microwave signal. We know we have to apply the right amplitude, duration, phase, and frequency. But how to address many qubits? Well, the idea is to take the system that we use for a single qubit and replicate it for 1, 2, n qubits. Tune each of these qubits to a different frequency. Tune the microwave drive for each of these qubits to the frequency of the specific qubit, so that we can sum up them up all together and send them through the same coaxial cable. So we can have one cable for multiple qubits, since each of the qubits is addressed on a single separate distinct frequency. What is important to realize is that for each of the qubits, we need to keep a separate oscillator that keeps track of the phase of the single qubits. We cannot, in any way, stop these oscillators, because we may risk to abruptly change the axis of rotation of a specific qubit. Therefore, it is important to have n different oscillators for n qubits. However, having n different microwave oscillators in the same system can become a nuisance. So it's much better to use different oscillators for each of the qubits, but also have them oscillating at a lower frequency. Implement them in the digital domain, as shown here, feed each of them to a digital multiplier, and then to the digital to analog converter, and multiply the result by high-frequency microwave oscillator signals. In this way, we can sum and send them through the microwave coaxial cable. By doing so, we obtain exactly the same signal, and we only have one high-frequency microwave signal that needs to be distributed in our system. We still would have to distribute this microwave signal all over the system. An improved solution would be to sum up the qubit signal in the digital domain, send them to a digital to analog converter, and then multiply a single signal by our microwave oscillator and send it to the coaxial cable. In this way, we obtain a very simple system in which we have a complex digital part for qubit 1, qubit 2, up to qubit n, which are shown here in different colors, and a simplified analog RF part, including one digital to analog converter and one RF oscillator. So we have obtained a system with a complex digital section, but that can be handled with today's technology, and a simplified analog RF section. This enables us to implement the microwave drive for many qubits on a single coaxial line. The only remaining step is to make sure that such a system can fulfill the specification that we have talked about before.